I'm going to start this video by saying something that you may not agree with, but of course I'm going to try to convince you. I like teaching Euler's method before I ever teach any analytical methods to solve differential equations, like separation of variables, integrating factors, and all of that good stuff. That is because I think working through Euler's method and doing a bunch of exercises using it gives us a real good feeling about what differential equations are actually about. So it helps our conceptual understanding of what is this object we're working with. So I think that if the students have a chance before that to work with Euler's method and sketch little approximations of the solutions, and that increases the probability that some of them will go like, wait a minute, but how would I do that for real without just being a numerical approximation? That may just be a fantasy in my mind. It's completely possible that studying Euler's method does not make any students ask any questions. But if they do, then I have an answer for that. Oh, you want some analytical methods? Okay, so check this out. Sometimes the variables are separable. So in that case, you can go and then I teach the other stuff. So maybe I'm just fantasizing that students would actually ask, how do I solve these things for real? But I'm not sure, at least in the context of the IB courses, this is high level content. So we're talking about students that are naturally inclined to enjoy math. So maybe they will ask. And I like teaching Euler's method first. So let's talk about that in this video. I'm not going to do any analytical methods today. I have another video where I do that to a bunch of equations. I'm going to link that in the description of this video. But as for how to teach Euler's method itself, that is something that I have changed my mind from how I used to teach it. Because I used to think that it was super important to stress the computational part of it. Like numerical methods are important because we can program these things into a machine so that the machine can do all the repetitive calculations for us and we will get a really good answer in the end that we didn't really have to work that hard for. We just understood the numerical method, but we didn't actually calculate anything specifically. We just typed a program into a machine. Now, of course, that is super important. This is why numerical methods are good. This is why machines can do so much stuff for us. But I think that this is important as a conversation. I used to put a lot of value in class into getting the students to actually do this, to actually program the repeating algorithm that you can then say, now run this 100 times. And in the case of the IB courses, that means doing it in the TI-84 calculator, which I am going to do in this video. But today I think that at least for the AA course, it is not really necessary for the students to learn how to do that. We will see in the examples that I'm going to go through that the exam questions tend not to ask for a big number of steps. So I no longer think it's very important to program the TI-84 to do it repeatedly by itself. The problem with that was that I think it was just scary for the students. It felt like that was a big focus of the Euler's method content. I have to learn how to do this complicated programming thing. And that shifted the focus away from actually, what is this method about? What are differential equations about? What am I doing? So I'm going to actually do both things in this video. First, I'm going to go through the concept of differential equations, and then I'm going to do Euler's method for the AA course, which doesn't require programming the calculator. But the AI course is a little bit different because the questions are really expecting you to do more computationally with Euler's method. So for that context, yes, I'm going to show you how to do that in the TI-84. Let's begin by talking about what a differential equation is. And don't worry about the scary picture just yet. I will explain that in a minute. So first of all, when we say equation, we are used to thinking about things like this, for example. It's an equality that depends on a variable, and we are trying to find the values of the variable for which that equality is true. When we're talking about differential equations, of course, there needs to be a derivative there. That's why it's called differential. But the more important thing that you need to remember about it is that the solutions that you are looking for are not values of x. So x is not the variable in this equation. What you want to find is functions. F of x is the variable here. We're trying to find functions so that this equality is true. The derivative of the function at any point is the value of the function plus x in this example that I'm working with. And just like in the traditional equations, you don't need to have just one solution. In the differential equations, you're usually going to find infinitely many solutions. It is a family of functions, all of which satisfy this equality here. Which brings me to the picture that we are looking at. This is just the coordinate plane. You have the horizontal variable x and the vertical variable y. And at each point, you are also seeing an arrow. This arrow represents the derivative of the function that one of these functions that are solutions to the equation, the derivative that it needs to have if it passes through that point. Because like I said, it's a family of functions. It's not just one function. So it's going to turn out that in every point of this plane, there is one of the solutions is passing through that point. And it is passing with this slope. So this picture is called a slope field. For example, if it passes through this point here, then it will pass with this tangent line. And if it passes through this other point here, then it's going to pass with this tangent line. These are not necessarily the same function because there are infinitely many functions in this family, but for all the points, the function that passes through that, the solution to the differential equation that passes through that point needs to pass with that tangent line indicated in the slope field. So the first exercise that I like to have my students do when we study this is to just try to sketch by hand. You'll have this image printed on paper, then you choose on the left-hand side here a point to start with, and just try to sketch a function following these arrows. You can sketch many different ones depending on which point you choose to start. And I think it's important to do this exercise with students at the beginning of studying this topic of differential equations, because it turns out that doing this is very intuitive for a lot of people, but for others, not so much. Other people get confused as to how do I know which way to keep sketching. It's something that you get used to after you do it a bunch of times, so it's worth spending some time doing that, because this is really what a differential equation is. It is a function that is trying to go somewhere, but it doesn't have the freedom. It has to follow what the equation tells it that the derivative needs to be. And that is changing at each point. When you move a little bit, then there is a different derivative, and then you have to follow that other direction, and so on. So there are a bunch of different pictures here in this file, and I am going to link this PDF in the description of the video, so you can print it out if you want to try to do it on paper, or you can just sketch on a screen like I'm doing here. Some of them are really crazy. Let's try to do this one. I'm going to start with a point here, follow this arrow. Something that is important to mention as well is that we are seeing a finite number of arrows in the picture, but conceptually, all points have an arrow, okay? And so if you are at a point here where there is no arrow at that exact point that I'm sketching right now, you can kind of just look around and see what the other arrows around it are doing, because it's not going to be a crazy difference. So in this one, I have an arrow pointing up here and an arrow mostly horizontal there. So something in between. It's still going up, but not as strongly as the arrow under it is showing. So you kind of average out the arrows that you can see around it, because this really is a continuous field of arrows. So something interesting that I notice when I have students do this exercise is that not everybody has the tendency to try to sketch smooth functions like I was just doing. It's about 50-50. Some people do it that way, and other people just take the arrow at the point where they started and try to go on a straight line following that arrow, sort of until you find another arrow. Then at that point, they change direction and draw another little bit of a straight line. And again, so they, instead of drawing a smooth function, drawing more like a collection of segments. But in the end, it doesn't really make that much of a difference, right? What I just did here looks pretty much the same as I was doing before. But this second way that I mentioned of doing the sketch is actually very, very close to what Euler's method is about. So first of all, let me just change the notation a little bit for my differential equation. I don't want to keep calling it f of x like a function just because that is clunky notation. I want to instead use just y, because y equals f of x is how we draw functions. And the important thing here is that the differential equation gives us a rule that connects the derivative of the function at each point, which are the arrows, to the coordinates of the point, which are x and y. In the case of this example, this is the relationship. It's that the derivative needs to be y plus x. This happens to be the example that we are looking at right now. But of course, the right-hand side of this equation is going to change with each example. So Euler's method is identical to what we were just doing, but instead of drawing, we are going to calculate coordinates of points. So you can choose a point to start. Let's choose a point on the left side of our image here. The coordinates of this point are -2 and 1.4. I'm calling the point P0 because I'm going to make a sequence of line segments, so I need the sequence of points are going to be P1, P2, P3. And the first thing that I need is from that initial chosen point, I need to figure out, according to this differential equation, what is the slope of the line segment that I need to draw here. I'm calling that m0, and in the case of this differential equation, all that I need to do is add up the two coordinates of the point. So that makes m0 -0.6. The next thing that I need to do is to decide how big of a line segment I am going to do. Usually in exam questions, this is determined for you, they tell you. But the smaller that the line segments are, the more closely this collection of segments is going to be representing the actual smooth function that is the solution to the differential equation. So in the case of this example, I can see that between -2 and 0 here, so in a space of 2 units, I have 10 arrows in a horizontal line. So that means that each segment is going to be 0.2. And it's usual to use the letter h to represent that distance. Okay, now what I want to do is to follow this line segment for a distance of 0.2 and figure out the coordinates of point P1, which is the next point. The x-coordinate, there is not much to do. It's going to have to be -1.8 because this is how much we decided that we're going to use as a step size. And now I need to use this length together with the slope of this line segment, which in this case is -0.6, to figure out how much the vertical coordinates have changed. And in this case, it is -0.12. Well, slope equals rise over run. So rise equals slope times run. That's all I'm doing here. So the y-coordinate of P1, we start from the 1.4. That was the coordinate of P0. And then we're going to subtract 0.12. So that is 1.28. And from here on out, the method continues by just doing everything over and over again. Now that we are at the second point, we need to figure out what is the slope of the next line segment that we are going to draw starting from there. And to calculate that slope, we are going to use the differential equation again. In this case, negative 1.8 plus 1.28 is negative 0.52. So now we use that to find the coordinates of the next point, which is the point P2. The horizontal leg here is never going to change throughout the whole problem, so this one is also 0.2 because the horizontal lengths of the line segments are all going to be the same. And again, in order to find the length of the vertical leg in this triangle, it is just the run times the slope, which is going to give us the rise. And putting all of that together, you get the coordinates of point P2, and then you do it again and again, however many times is necessary in order to reach as far to the right as you want to go. Now, obviously, there is a problem here because I just did 2 steps, and so far I was just doing calculations in my head, but they are clearly getting more and more difficult because we have to deal with small numbers, because if our step is too big, we are ignoring all of the change in the slope field that happens from this point to this point. So the smaller the step size, the more precise your approximated answer is going to be in the end. But small numbers are difficult to work with. They have more and more decimal places as the calculation progresses, which is why doing calculations in your head like I was doing so far is not a good idea. You're going to be using your calculator, obviously, to do this type of calculation in the problems that you're going to solve. And like I mentioned in the beginning of the video, in real life, of course, it is a good idea to automate this. You don't want to do even 10 steps, like doing the same thing 10 times is boring, is not a thing that humans are made for, but machines are. So automating this and programming the machine to do all of the 10 or 100 or however many steps there are automatically is a very good thing. But I am not going to do it right now. What I am going to do right now is to go through one of these examples here. And of course, this was not the entire question, okay? This is part A, asking us to use Euler's method to do something with this equation. And this was a much longer question. It had a part B, C, D, but we are not interested in any of that right now. So I took away the rest of the questions and I brought 3 examples here, which are all the same, really. It gives you an equation, a starting point, the length of the step, and then he tells you how far he wants you to go. So because I'm going to keep my calculator on the screen for most of the time, I have just copied to this side the equation that we're going to be working with, which is this one right here. I've also rewritten the equation in a way that I think is going to be easier to type. So the point P0, our starting point, that in the example with my picture that I was doing, I said you can choose the point where you start. Of course, in an exam question, you don't get to choose because he's going to tell you the point. So he says that the differential equation is this, with y equals 2 when x is 1. So that is the point 1, 2, which is our initial point P0 right here. I also mentioned that he was going to tell you the step length. He's using h equals 0.1 this time, so I wrote it down here so that I don't forget. And we are starting at x equals 1, and we want to go all the way to x equals 1.4. So that's going to take us 4 steps of length 0.1. That's why I wrote down here 4 steps. And now the first thing that we need to do is to figure out the slope of the line segment at the point P0. This is where we start using the calculator because now we want the value of the derivative, which is the y prime, but when x is 1 and y is 2. So that is 4 plus 2 squared over 1 squared, and then minus 2 over 1. That is, according to the differential equation, y prime at the point P0, giving us a slope of 6. So now I need to figure out the coordinates of the point P1. The x-coordinate is just 1.1 because we started at 1 and used the step size 0.1 to the right. And the y-coordinate is going to be 2.6. In this case, it was a simple calculation, but it is how I was describing it before. Slope equals rise over run. In this case, the slope is 6, so the rise is 0.6. And as we started at 2, now we move to 2.6. Okay, so from point P1 now, we again need to find the slope at that point by plugging in these new coordinates, 1.1 and 2.6, into the same differential equation to find out the new value of y prime. So you can just type that in there, and the new slope is this. This time is not such a pretty number, but it is what I am going to use to find the y-coordinate of P2. Well, I have the calculator open, so let's not try to do this in my head. It's 2.6 plus this number times the step size. So 3.32 is the y-coordinate of P2. Let's go ahead and do it again. So you see, it is getting a little bit boring at this point, but we're almost finished. We've already done it twice, and we only need to do it twice more because the question asked for 4 times. So let's just keep going. We're going to plug in the coordinates of P2 into the equation to find the new slope. We're going to take the y-coordinate of the previous point and add to that slope multiplied by the run. And then we're just going to do it one final time to finish this question. Okay, that's it. The problem is over. Something like this will be 4 or 5 marks. Could I have been more careful with the significant figures through my process? Sure, I could have, and I probably should, because I was typing 4.21 when I had the 4.20877 at the line right above it, and stuff like that. But this is not exclusive to Euler's method, right? This is just the standard level of care that you need to have with significant figures in any content that you're using your calculator for. So I'll let you handle that. The point is that the question is finished because the question was to find an approximate value of y when x is 1.4. And we have found that it is 5.33. That's the approximate value of y when x is 1.4. I'm going to leave these other 2 problems here on the screen for you to practice a little bit. I am not going to do them because they are exactly the same and wouldn't add anything to the video, but feel free to put your answers in the comments so that you can compare your numbers to the other numbers that other people find. And that is really all that an AA high-level student needs to know in order to handle the Euler method questions in the exams. But if in case you are using this for something in your IA in a practical application, you're probably going to need to do more than 4 steps. Or if you're just curious about how to automate this stuff in the TI-84, that is the next thing that I'm going to do now. Okay, so check this out. You know this button here, the y equals, where you usually type your functions to graph, right? That's not what we want to do right now. But if you go into the mode button right here, there is a line here where it says function right now, and you can change that to say sequence. That is going to make it so that the same button, the y equals button, now has this. So these 3 types of sequences here, you can use any one that you want. Maybe this one is slightly more easy to work with. What we need to type here now is to generalize the calculations that we've been doing explicitly for the numbers that we had at each point. We need to write that in a more general way with variables, and the variables are going to be these u and v that the calculator wants. So I started by calling my initial point P0, so I'd better say that the smallest n here is 0. And these variables that he wants to use, u, v, and w, we're not going to use w right now. But unfortunately, we can't change their names. So let's just remember that u is going to be the x coordinate of the points, and v is going to be the y coordinate of the points. So I've put the 1 here and the 2 here to start at the point P0, which is the point 1, 2. Now, u of n plus 1. What I need to type here is how do I figure out the x coordinate of the next point, n plus 1, if I have the x coordinate of the current point, which would be un. How do I find that? It is by adding h. So it's the un plus 0.1. That's what I need to type here. And if you've never worked with this before in your TI-84, then there is no reason why you would have ever noticed this. But the variables u, v, w appear right here in the blue buttons above the numbers 7, 8, 9. So in order to type the sentence u of n plus 0.1 that I want right now, I need to use the button 7, but it's blue, so it's second 7. Now I'm going to open parentheses, and I want to put the n inside. The n is a variable, so it's the same button that you use for the variable x all the time. It's this button right here. So now you close that parentheses and you add 0.1. That's it for the x coordinate of the points. So you start at the first x, which is 1, and then after that, each one is just going to take that and add 0.1. So it's going to automatically do all of the other ones. But now we need to worry about the y coordinate, which starts at 2. But how were we calculating that y coordinate before? We would start at the y coordinate of the previous point and then do a little bit different according to the slope of the triangle that we were looking at. So first we're going to start by typing v of n, which is the y coordinate of the previous point. So now we're going to use the button 8 with the second 8 to get that v, open parentheses, variable button to get the n, and then close parentheses. And now we need to add something to that. What we need to add is the rise of the triangle that we've been talking about. And I mentioned a couple of times that rise is run times slope. The run is the step size, which is the 0.1 that we've been using. And then we need to multiply that by the slope. And now the slope depends on the point. It's not always the same, but it depends on the slope in a very specific way, which is the differential equation, which is 4 plus, well, it's that sentence that I've been copying from at the top of the screen over there, right? So 4 plus y squared. What is y? Y is the y coordinate of the previous point. So in the language of the variables that we're using right now, that is v of n. So I take that v of n and I square it. And now I need to divide that by x squared. But what is x? It is the x coordinate of the previous point, which in this language is u of n. I squared that as well because I am copying from my differential equation, and the next thing that I copy is this minus, and now I need to type the y over x to wrap up my differential equation. The differential equation is what tells us what the slope is, so I have the slope typed here. I've multiplied it by the run, so this is the rise. The rise is being added to the previous point where I was at, so that is the new value of the y-coordinate of the next point. That's it. That should be enough. So this is equivalent. Remember, we are in the same y equals button as we usually type functions. So that is equivalent to typing a function. The next thing we usually do after we do this is to graph the function. So we are going to do something in that graph button right now. But I'm not particularly interested in graphing it. What I want is the blue stuff on top of it. I want to see a table of values. Here is the table of values. The point 0 is the point 1, 2, where we started. The point 1 is 1.12.6, which is the same value that we had before. And comparing the next points, you see that it is correct as well. So you have 1.2 and 3.32. Then you have 1.3 and 4.21. 1.4, I'm getting 5.34 here to three significant figures, and originally I had 5.33, but that's just because I wasn't careful with my significant figures, which is one of the advantages of typing it in this way, because the calculator is automatically going to be very careful with the significant figures. Another advantage is that you get a lot of steps. You didn't have to have all of that work just to get 4 steps. You get, I don't even know how many you have, but it's a lot as you scroll down. And finally, the biggest advantage is that, remember how I said that the smaller the step size, the better this approximation would be for your actual function that is the solution of the differential equation. Now that you've typed this, it's very easy to change the step size. Let's go back to that screen by clicking the y equals button. To change the step size, all that we need to do is to change the 0.1 here. So maybe I want to use 0.01 instead, a very small step. So let's just put an extra 0 here and an extra 0 right here. And now we just run it again by clicking on the table. Of course, if I want to find my 1.4 now, this doesn't just take 4 steps. I have to scroll down a lot more because it's going to take 40 steps, but it's eventually going to get there. So a better approximation for the value of y when x is 1.4 that the question was asking about, better than 5.33 or 5.34 would be the approximation 6.11. That is how different this is. Of course, the answer to the exam question was 5.34 because he specified that you should use a step size of 0.1. I'm just saying that in reality, that is not the value of that function, of that solution to the differential equation. 6.11 is going to be a closer approximation, but it's also not the exact value. The AI high-level course is more complicated because they do systems of differential equations where you have more than one function interacting with each other and you have some information about their derivatives. This question here is a very good example of this. The context is a predator-prey model, which is also very common, but I'm not going to get into the details of it right here. The thing is that you have two functions, the m and the s, and both of those are functions of the variable t. That's why you can see on the left that it's the m dt and the s dt. It's not like m is a function of s or vice versa. That's not the way that they interact. They interact through the differential equations for their derivatives, which are these. The alpha, beta, gamma, and delta there are just constants. He's telling us the values of the constant right here. But the thing is that in this context, we really do have 3 variables, right? One is the independent variable t, and then m and s as dependent variables. So that's why it's important that the calculator has also those 3 letters, u, v, and w, because this time we are going to use all 3. I'm making a choice here to use u as m, v as s, and w as t. So I wrote it down there so that I don't forget. And I'm also going to write down the system of equations so that I can put the calculator on the screen. As I do this, I am going to copy the numbers as well because I'm going to need them. So I've substituted the parameters that the question gave me into the equations. Now I'm going to copy down the initial conditions as well, the values of m0 and s0. I'm writing it this way just to remind myself that these things are functions of the variable t, and that when t is 0, those are the values. And the question is also giving me the step size, which is 0.1. So what are the things that he's asking me to do in this question? Part A1 is just asking me to write down expressions for the next point in the sequence. This is just him confirming that I know how Euler's method works. He is going to give me 3 marks just for that, even if I don't get any numbers correctly in any calculations. So I'm going to write it down here. The next value of m is going to be the previous value of m, which is mn, and then plus the difference, which is the step size times the slope of that particular function, which is the m prime given in the differential equations. So the step size is 0.1 because he gave me that. And then I'm just going to put the information from the differential equation here. That sentence turned out to be a little bit longer than I was expecting, so I moved it to the next line. So that is just copying the information from the differential equation. Well, kind of, because the question asks for it in terms of mn and sn. So you can't just put ms like in the differential equation. You just have to remember to put that in terms of the previous point in the sequence. And then you do the exact same thing to write down the sentence for sn plus 1 as well. And those sentences are exactly the things that we are going to type in the calculator, except that in the calculator, those things are not called M and S. U is M, V is S, and W is T, like I wrote in the top right corner here of the screen. And the question is asking us to find the mackerel population, so that's the M, after 1 year. So since the step length is 0.1 years, that's going to take 10 steps, and he is asking for M10. He could have asked for both, but he didn't, so but we do need to calculate both because one depends on the other at each step. Okay, so let me clear the previous equation that I had here. Let's begin by putting the initial conditions. U is m, and the initial m is 5.7. The initial s is 2. What a coincidence. And now we need to look at w as well, because w is time, and the initial time is going to be 0. Now let's type the next value of m. We have to start with the current value of m, which is un, and then we have to add the step size multiplied by the differential equation, which is 0.549 times m. M is the current value of m, so it's un as well. And then the term with the 236 is times ms, so that's un times vn. That is a very long sentence, and please be careful not to type any number wrong, because it was going to be a pain to find where the mistake is if you do make a mistake. But this is one of the reasons why in this scenario, I think it's better to actually do the programming in the calculator, because you don't want to be typing this over and over again. It was fine for the AA exercise that we were doing before, but in this case, it is just too much to be doing over and over again, especially because notice that he did ask for 10 steps. 10 is bigger than 4, so it seems silly, but it is a difference there in the amount of work. So now I'm just going to do the same thing to V. We're going to start at Vn and then add that to the step size times the S prime, which comes from the differential equation. And now we also have to type an equation for W. What is that? That's not in the system that he gave me, but W is time. So time is growing linearly. It's just the next time in the sequence is the previous one plus the step size. So that's it for the equation of time. And now the question wants M10. Well, I think I'm ready to go to the table of values. It took a longer time to calculate that because it is more calculation than the previous example, but also because accidentally I asked him to go all the way until 40, which I didn't need to do. But that's okay because I can just scroll up, and the value of M10 is 6.1161. Another hint that this question is different from the previous one and what you are expected to do in your calculator is that the other question gave you 4 marks to do 4 steps. So that is enough marks for you to have time to do it by hand like we did. And in this part, it was 2 marks for 10 steps. That would not be coherent with the time that it would take to do it by hand. So in this question, you are expected to be programming the calculator like we are. And also, part A3 is asking us to do something completely different than before. Use Euler's method to sketch the trajectory of the phase portrait. This 4 and 7 and 1, 5 and 3 are just the window in which he wants this sketch. And then over the first 9 years. So 1 year is 10 steps. If that wasn't enough, now he wants 9 years, which is 90 steps. Okay, but what is a phase portrait? Here is the thing. M and S are functions of time. I'm just drawing a random thing, okay? This is M and this is S. But this is not what he wants us to draw. Remember, we have 3 variables here the whole time. They are time, M, and S. But a phase portrait is not the graph of the functions M and S. The phase portrait is a graph that has M in one axis and S in the other axis. And where is time? Well, time is not here. Each time is going to give a point in the sketch. An interesting observation is that we can't draw this kind of sketch for any system of differential equations. It has to be a system of this kind right here, where notice that the right-hand side of the equations don't depend on t at all. They could, in theory. Just like in the previous example, the f prime depended on both f, which is y, and also on x. So that is a valid thing to calculate, but you just wouldn't have the opportunity to draw this kind of sketch. Because if, as well as depending on the current values of s and m, the derivative also depended on time, then being at this point at time 0 would maybe make this function, but maybe being at the same point on a different time would make a completely different trajectory. So you can't sketch because it depends on time. But anyway, let me show you how to do that in the calculator. Because the whole time this has been analogous to graphing functions. This is where you type the functions. The window, you're also going to have to put the window that the problem gave us. And notice that it is the same window button that I clicked as you usually use for graphing functions. But it's looking a little bit different now because we are in the sequence mode. We are not in the functions mode. So now the window is asking us for an n min, which is 0, but the n max that I want is 90. This is how many steps that I want to put in my sketch. X min and X max are what you expect. This is going to be 4 and this is going to be 7. And the Y min and Y max as well. This is 1.5 and this is 3. But if you just do this and then click the graph button, this is not what you want to see. This is wrong. What he is attempting to do here is to have n, the step on the horizontal variable, and then plot u, v, w separately like that. That is not the kind of graph that we want. What we want is the phase portrait that I just talked about, so we need to tell that to the calculator. And the button that's going to do that is the next one here. It's this blue thing that says format. So you click the blue and the zoom. The first line here is what is going to determine that. Time, which is the default setting, is what he's drawing. The horizontal axis is time. Well, he doesn't know that I want W to be time, right? So it's time for him, like the index of the sequence. I don't know what web is, but UV is definitely what I want because I want a phase portrait of M and S, and I determined in the beginning that M was going to be U, S was going to be V, so this is the setting that I want here. Now I can click my graph button, and this amazing thing comes up. I find this very, very beautiful. In order to complete the exam question, you just copy this image into the paper. But for our own entertainment here, maybe we want to see what happens with more steps, right? 90 is not enough. So let's put 500 and see where this thing goes. Look, it spirals out, out, out. Very, very beautiful. I am often impressed by the things that my calculator can do. Anyway, in terms of exam questions, this kind is going to be very common. It's a predator-prey model, like I said. And the other type of problem that is common is this type here, where you start with a second-order differential equation, which is one that involves the second derivative as well as the first derivative. And then there's an easy substitution to use to turn that into actually a system of two differential equations of the same type that we were working with before. But this is a show that question, so as usual, you can skip that if you just don't want that 1 mark, and you can keep doing the rest of the items in the question. But that's not the equation that he is going to ask us to use Euler's method in. He's going to ask for Euler's method in this equation here, which has a slight difference to the original one because now the right-hand side is 3t plus 4 instead of being 0. And the thing is that you need to know exactly where you are going to put that 3t plus 4 here, because this first line of the matrix that just says that dx dt is y, that can't change. So we're going to put a 0 here in the first line of this new term. What is going to change is the second line, because dy dt, which is the second derivative of x, is this multiplication here, which gives us this part, and then plus 3t plus 4. And listen, I just want to point out here that I can't explain all content in every video, so this part didn't make any sense to you if you don't know about matrices yet, because I am assuming this knowledge for this part of the video. So I am going to now rewrite this system of differential equations in the same language that I was using before. So the first line is telling me that x prime is equal to y, which we already knew. And the second line is telling us that y prime is equal to minus 6x minus 5y plus 3t plus 4. So again, we have 3 letters here to use in the calculator. So let's say u is going to be x, v is going to be y, and w is going to be t. I think that is the most similar to how we used it in the previous problem. But notice that in this example, we do have the variable t playing a part in the system of differential equations together with the y and the x. So like I mentioned, it's not that this is forbidden, is that this type of question had better not ask you to draw face portraits. So anyway, the rest of the information in the problem, we start at t0 with the particle at the origin. So all the initial conditions are 0. The step length is 0.1, and he wants to go to t equals 1, so that's 10 steps. And then I'm not going to plug that in the calculator. I'm just going to leave that as an exercise for you. The question is, find the displacement of the particle when t equals 1. So what I want you to put in the comments is the x and the y at t equals 1. And displacement is probably the distance between that point and the origin, right? Let me know what you think about that.